Okay, let's say we have R equals 4 cosine of 3 theta. How do we graph that? Well, you could make tables, and you're going to choose theta values. So if the cosine of 3 theta goes like, maybe pi over 4, pi over 2, and so forth. So theta would be like pi over 12, 2 pi over 12, 3 pi over 12. Of course, those reduce. Okay, that makes sense? What you really want to see is first thing is it goes through a complete cycle as the argument goes from 0 to 2 pi, right? In other words, as 3 theta changes by 2 pi, you get a cycle. So as theta changes by pi over 3. Thus constructing this graph, then I would use that fact and say that, well, here's 2 pi over 3. Here's 2 pi over 3, right? And here is 4 pi over 3, which is double this. And of course, this axis is theta equals 0. 4 theta equals 6 pi over 3, which of course equals 2 pi. Of course, we know this is 2 pi, but we want to note that that's a multiple of 2 pi over 3. I mean, it has to be, but just kind of brings things full circle. Now, we know that. We also know, I hope, that the graph cosine of theta, cosine of 0 is 1. So we have a point here, right? And then the cosine of pi is -1. Okay? Cosine of pi over 2 is 0. Well, as theta goes from 0 to pi over 2, we did this in class last time, we get this. We go from 1 to C, from R equals 1 to 0, right? And you could draw some lines there, some radial lines, and see that R keeps decreasing and approaching 0. And we said that that's a circle, and it's easy to see that that's a circle. And then as we continue to go out here, the cosine takes negative values and comes back around to 0 here, okay? Or comes back around to -1, which takes you to 0. So as theta goes from 0 to pi, we go through a complete cycle here, right? We go through a complete circle. And it is a circle, as you can easily prove. Okay? Well, what's going to happen now, though, is that theta, as theta goes from 0 to 2 pi over 3, well, as theta goes from 0 to pi over 3, halfway to 2 pi over 3, the cosine is going to go from 1 to 0 and back to 1. Or, sorry, from 1 to 0 to -1. Okay? So if this pi over 6 here, and pi over 3 here, from 0 to pi over 6, the cosine of 3 theta is going to go from the cosine of 0 to the cosine of 3 pi over 6, that's pi over 2, right? So cosine is going to go from 1 to 0, S theta goes from 0 to pi over 6. Does that make sense? Okay. And then as theta goes from pi over 6 to pi over 3, the cosine is going to go from 0 to -1. So corresponding to our angles here, we're going to be going in the negative direction. By the time we get over here, we're going to be by 4 pi over 3, a little too steep. Be more like here. This is going to take us along a loop like this. So this is the loop for and I did that one. Again, as theta goes from pi over 6 to pi over 3, cosine is going to go from 0 to -1, not all the way back to 0. So it's going to go from 0 to -1. Okay. So this much of the curve corresponds to theta from 0 to pi over 3 takes 3 theta from 0 to pi, and we get that much of our curve. Now, as we go from pi over 3 to pi over 2, the cosine value is going to go from -1 to 0. So cosine goes from -1 to 0 along these lines. Of course, that's going to take in the negative direction. It's going to come back like this. And then as theta goes from pi over 2, where 3 theta is equal to 3 pi over 2, right? To 2 pi over 3, where 3 theta would be equal to 2 pi, your cosine values are going to be positive again. And you're going to come around like so. So that's for one section of the curve corresponds to this. Now, we go through all the same values again. Cosine is going to go from 1 to 0 to -1, back to 0, and end up at 1 as we go from here down to here. Now, you might have to think, a good bit about it. This is the way you might want to think about the graph. And I'm going to run out of colors here. But that's going to take us around here. So cosine from pi over 3 to 5 pi over 6 is going to do this. This curve should be tangent to that line. I just drew it. I was a little careless. But then it's going to come around. And these are the negative values. Going to come around to this. And then it's going to come back. Cosine will come back to 0. Sure, is correct. These are negative values. 5 pi over 6 up to 5 takes us to 1. Yeah, it's going to come around. I'm just convincing myself here. that we've got this section of the curve that corresponds to oh, 2 pi/3 to pi, you get the purple section of the curve. And then we get an orange section that goes down in tangent to this. And then comes back and fills in this loop. Comes down like this, and then retraces this. Then as we go from 4 pi/3 to 2 pi, we retrace this part of this loop and then this part of this loop, and then we come back and finish it. And I'm not going to go into detail on that. You can kind of figure that out. Oh, I don't quite have that drawn right there. They're kind of intersecting where they should, but you get the idea. Okay. I should have drawn the line. If you do sine of theta, you get a cardioid. If you do sine of 3 theta, you can kind of think how that works. Okay. The sine of theta starts at 0. That's the cardioid isn't drawn particularly well. Well, it's not that well. But sine goes from 0 to 1. And then back to 0. I think maybe that has the cardioid on the too quickly oriented model. Kind of rotated this way. But there we have it. Okay, just one way of thinking about these things. What I did here was I broke this into 3 subcycles. You have a graph that kind of looks like this for every subcycle. Okay. Actually, that white segment should have been where the blue segment is. Anyhow, made a couple mistakes there. I just didn't draw my lines carefully enough. Mainly, I should have drawn these radial lines here on the other side of the axis, but I know I was going to want to use them when I was down here, so I chose not to draw them. And then it looked wrong picture. But you get a rose, and it kind of looks like yes, it's drawn accurately. Actually, that's really neat. I've got too many of them. Lose track of what I'm doing, but kind of that shape. You've seen the shape, okay? Makes sense? And you can do symmetry tests and stuff like that. We're going to work with symmetry, but we'll talk about it with respect to the coordinate systems when we actually get to it. Now, the biggest thing you want to take away for the purpose of this course is a change of coordinates. Okay. Remember that you got like r equals x cosine theta. And it's x equals r cosine theta. Told you just what unit to take it. And then y equals r sine theta. And then you have r equals x squared plus R squared. R squared equals X squared plus Y squared. Theta equals the inverse tangent of Y over X. If X is negative, you got to add pi or 180 degrees. That's because the inverse tangent, as I hope you know, gives you an angle between negative pi over 2 and pi over 2. The angles are always to the right of the y-axis. Okay? So if you happen to have a negative value of x, the tangent only gives you angles from negative pi over 2 to pi over 2. You're going to have to add 180 degrees so you can get from pi over 2 back down to negative pi over 2 and get the entire cycle. Okay? So you can easily enough change an equation in polar coordinates to rectangular or equation in rectangular coordinates to polar. Got to be a little careful about our tangent, but draw a good picture. Like I almost do. Well, at this point, before we really use it, we're talking about polar and rectangular coordinates and stuff like that. So the text has chosen to introduce cylindrical and spherical coordinates. Okay. So it's, I guess, as good a place as any. You don't really use them for at least 2 or 3 chapters. Okay, but you might as well get used to them at this point. Usually they're introduced at the point where you have to actually apply them to surface integrals and volume integrals and stuff like that. It's not a bad idea to do it here, so you get used to it before you have to use it a lot. Cylindrical coordinates are pretty easy to understand. So now we're going to go into 3 dimensions. We haven't done that much in 3 dimensions. Much of what we've done extends into 3 dimensions. Okay. So if we've got our X, Y, and Z axes here, and we've got a point in the X, Y, Z plane, let's say the point is here. Now you don't know where that point is until you project it down to the X, Y plane and then project over to the coordinate axis. Now we know what the X, Y, and Z coordinates are. Now the Z coordinate, well, we could draw kind of a diagonal line here and then a line parallel to this one, which shows us where we are on the Z-axis, right? That makes sense? Okay, so all these angles are right angles. Here's a right angle. Here's a right angle. Here's a right angle. And of course, here's. You understand that picture? Can we visualize where that point is? Okay. If the origin is here, and the x-axis goes this way, the y-axis goes that way, and the z-axis goes that way, that point is this far along x, this far along y, and this high, which corresponds to degree on the z-axis. Okay. There's another way to specify this point. Okay. This point lies directly above the point down here. It has polar coordinates. Okay, well, rectangular coordinates of this point are x, y. Polar coordinates are theta. Now, what's r? Well, r is the distance from the origin to this point. So right here is r. Make sense? And theta. Well, theta in polar coordinates is the angle with the positive x-axis drawn counterclockwise, which means drawn toward the y from the x toward the y-axis. So that theta is here. So the coordinates of this point rectangular is x, y, z. Cylindrical, it's r theta z. Where you see what r is, you see what theta is, and z is just z. That's pretty easy. Now, kind of shapes you get in cylindrical coordinates. Turns out that cylindrical coordinates are the most convenient coordinate system for things that have like axial symmetry. Okay, we'll see what that means in a minute. So you have x, which is r cosine theta. So you have y, which is r sine theta, and you have z, which is z. There's x, y, and z in coordinates r, theta, and z. Z is just z, and x and y are just what you get if you apply the same transformation rules you would for polar coordinates. Okay. And then, of course, in cylindrical coordinates, you have r and that is going to put plus and minus there, but that makes no sense. Then you have theta is the inverse tangent of y over x. Plus 5x is less than 0. Exactly the same relations between your x and y coordinates and your r and theta coordinates that you have for polar coordinates, because it is just polar coordinates in x and y. And then z equals c. Okay. And that's pretty simple. Okay, well, we'll draw you another thing. I'm still going to draw my x, y, and z axes. As well as my r theta and z. I'm going to pretty much repeat the picture I just drew. So here's my point. I'll label things in a minute. I'll lower my thickness a little bit. Okay, and the origin directly to that point. Not going to be R, it's going to be rho, which is the Greek letter that corresponds to R. So this distance is rho. And I don't like where I labeled that. I like the whoop. I don't like the. Okay, this is rho. That's your distance from the origin. The reason I don't like the way I labeled that, well, we'll see in a minute. Here's theta, same as it is for polar coordinates or cylindrical coordinates, okay? And then this angle from the z-axis to the radial line from the origin to the point, is phi. Some people pronounce that phi. Okay. I don't know why they would, because the Greek alphabet goes phi, phi, pho, fum, not phi, phi, pho, fum. Okay. So again, I don't like that rho. We're too close to the okay. So that question then is, R in terms of rho and phi is R equals what? Okay, now I've asked you to do that, and then I gave you a hint of this recorded. I said that, okay, here we've got a triangle involving rho and R. And it's a right triangle. Do we know one of the angles within that right triangle? One of the acute angles, of course, we know 90 degrees. Okay. And somebody said 90 degrees minus phi. Well, that would be down here because phi, 90 degrees goes from here down, well, from the z-axis down to any point in the plane, you got 90 degrees, right? Z-axis being at 90 degrees with the plane. I said, yeah, you can do that. Or you could just say that, well, this angle's phi. Okay, why is this angle phi? It's because this projection line here is vertical, so is the z-axis, so that the segment with length rho is the transversal of two parallel lines. And you have alternate interior angles. And I'm drawing it here where this thing's kind of flattened out. You're looking at it from this angle. Okay, here's your R. Of course, there's your right angle on tragus. And there's your Z coordinate. And here's your Z-axis. This projection segment is parallel to this. So this angle is an alternate interior with this angle. Therefore, they're equal. Now, my question is, how do you express R in terms of rho and phi, given that triangle? what's the relationship between R and phi and rho?
R,
Okay, so we got this triangle, there we have it, and we can see from this triangle that R is opposite angle phi, here hypotenuse is rho. So that rho sine phi equals R. Okay. That's the definition of a sine. So it's the opposite. Opposite over hypotenuse. Phi is the opposite over the hypotenuse. Sine of phi. And we get that. It's very straightforward. You should understand triangles well enough to just look at them and see that. Okay. But you can write it out. You want to get used to it. Okay. So R in terms of rho and phi is this. Now we want to do R, theta, and Z in terms of rho, theta, and phi. Well, theta is the same in both coordinate systems. So now we know what R is in terms of the spherical coordinates, and we know that theta is the same as it is in cylindrical coordinates. What about Z? Okay, so Z is the side adjacent to phi. So Z is going to be rho cosine phi. And then, of course, you can also write how much room I've got. Rho theta and phi in terms of R theta and Z. Rho squared is R squared plus Z squared. Phi in terms of R and Z is the inverse tangent, if you wish, of R over Z. And phi is, and I don't have to do plus 180 degrees if something is less than zero. Now, why is that? Something that doesn't seem right about it, but phi is between, actually phi is between 0 and pi. So you do have to worry about that 180 degrees. I'm just going to put etc. there. If Z is negative, you're going to have to add 180 degrees. And theta, in terms of rho, phi, and Z, you can look at this triangle down here, and that triangle would have R here. Now try to do something you don't do. Theta is equal to theta. Split. Okay. And then we can relate all this to rectangular coordinates. So now we see how to do cylindrical in terms of rectangular. We see how to do spherical in terms of cylindrical and cylindrical in terms of spherical. We still need to see how to do rectangular in terms of spherical or spherical in terms of rectangular. And I'm just going to write that down. It's pretty obvious. X equals, well, I mean, in the first place, in this picture, it's R sine theta, but R is rho sine phi. And I said sine theta and cosine theta, so it's rho sine phi cosine theta. You can see that as R cosine theta. R is just rho sine phi. Then you got to be able to see that. And then, of course, Y equals rho sine phi sine theta. And Z, well, is just real cosine theta, that's cosine phi. So there you have rectangular in terms of spherical. And I'll leave it to you to puzzle out spherical in terms of rectangular. You want to think through that. Your book is going to tell you. Here's a vector in three-dimensional space. Want to find a vector of magnitude 10 in the same direction. How do I go about doing that? So the strategy could be obvious. A unit vector in the same direction multiplied by 10. Well, the magnitude of this vector, 2 squared is 4, 3 squared is 9, that adds up to 13, add that to 25, you get 38. So U is going to be V, the magnitude of V, which could be calculated in various ways. I just used the Pythagorean theorem, but it could be V divided by the square root of V dot V. In any case, that's going to be kind of small, kind of badly. We just put the square root of 38 in the denominator of each of these. That's pretty obvious. That's easy. Okay, so looking at this rectangular solid, where this point is 490, this point is 4912. Okay. This point is 490. This point here is 4912. I've got my labeling all messed up. There it is. And that it should be clear that the vector from here to here is 4i plus 9j plus 12k. To start here, you got to go 4 units in the I direction, 9 units in the j direction, 12 units in the k direction. Okay. Now, if I want the vector from here to here, and unfortunately that vector goes behind my labeling, so be it. It's along this face of this rectangular solid. Okay. So we got to go from 490 to 0912. And why is this 490? Because this is 4912, but this is projected down into the XY plane where Z is equal to 0. This point here is on the back face of the cube, which is in the YZ plane where X equals 0. So X equals 0 back here, but Y is still 9. To get from the origin to this point, we got to go 9 units and then 12 units in the K direction. So 9J, 12K. But we can do this by subtracting coordinates. Okay, go from this point to this point. Our I component is going to be 0 minus 4. Our J component is going to be 9 minus 9. And our K component is going to be 12 minus zero. So I've written that out. There it is. Okay. Pretty straightforward. You do the cross product of that. Okay. We've already looked at cross products, and actually it hasn't even been introduced in the text yet. But as you know, you can do a cross product. We can do dot products of vectors. Okay. We could find the component of this vector in the direction of this vector. Okay, we do the dot product by the product of the magnitudes. The inverse cosine, we get the angle, get the projections, we get all that stuff. Same as we have already looked at. One other thing. Well, I got to mention more than one. How would you draw the equations? Sphere of radius 8 centered at the point 2, 3, -7. Now, what is a sphere? It's a set of points that are all at the same distance from the center point. Okay. So look at how I do this. Gotta start using numbers off it when they're hard to write down there. So, okay. If X, Y, Z is on the sphere, then the distance of X, Y, Z from this center point is 8, right? That's a no-brainer. That's what it means. Now, what's the distance of X, Y, Z from 2, 3, -7? Well, we could say the distance is the magnitude of the vector from this point to this point. Or let's say from the center to this point. So from the center to X, Y, Z is X -2I plus Y -3J plus Z +7K that's the magnitude of this vector. Okay. Well, we dot that vector with itself. There's the distance, and it has to equal 8. So I square both sides, I get X -3 squared, X -2 squared plus Y -3 squared plus Z +7 squared equals 64. And now I'm not sure, but it could be. If the camera zoomed itself in a little bit, so make sure we got the bottom of the screen. Okay. So that's typical equation of a sphere. And if you understand the equation of a circle in 2 dimensions, as you should from early pre-calculus, and if you don't, and if you haven't seen it since then, well, review it. It's really simple. Same logic, except you don't necessarily use vectors. We could also do this. With a rectangular frame. Let this be the point 2, 3, -7, and let this be the point X, Y, Z. Okay. What's the distance from here to here? Well, we could look at this diagonal along the bottom of the frame. And the coordinates of this point would be X, Y, -7, wouldn't they? Because presumably the lower part of this plane is parallel to the XY plane, perpendicular to the Z axis. So its coordinate is going to be the same as the Z coordinate of this point. Z coordinates will be the same. Okay. And that distance is, by the Pythagorean theorem, square root of X minus 2 squared plus Y minus 3 squared plus -7 minus -7 squared, but -7 is minus -7 is 0. So this thing has this length. And now we can look at this triangle here. And by the Pythagorean theorem, the legs are Z minus 7, that would be here. And square root of X minus 2. Well, if I apply the Pythagorean theorem, take the square of this and add to the square of this. Well, what's the square of this? Well, just X minus 2 squared plus Y minus 3 squared, right? And what's the square of this? It's Z minus 7 squared. So I'm going to have this square plus this square plus this square equal to the square of the hypotenuse. Hypotenuse is going to be the square root of that. So we could get the same whatever we call it, rectangular wire frame. Okay, makes sense? So I'm getting used to 3 dimensions, but vector operations in 3 dimensions are no different than what you've already seen. And what if you wanted to find the arc length of a curve in 3 dimensions? Well, in that case, you want to have it in parameters. You have X of t, Y of t, and Z of t, right? And your arc length increment would be square root of X prime squared plus Y prime squared plus Z prime squared, just like it was X prime plus Y prime, X prime squared plus Y prime squared when you did it last week. Okay, you just have a Z prime squared, and then it's integrate with respect to t. Now we can write that out formally. We don't have time. I'm not going to bother to do that today with 3 minutes to go. But I'm just saying that what you do in 3 dimensions is no different than what you do in 2 dimensions for the most part, except that you can do cross products that are in your space now, instead of perpendicular to the XY plane, okay? Which is in 3-dimensional space. That's about it. Now, there is more, you can express all these arc lengths and vectors. You learn how to do arc lengths in areas in polar coordinates, right? Well, now we're going to get to do them in cylindrical and spherical coordinates. But that's not coming up in this chapter, okay? In this chapter, all we've got left is reading this. Okay, all we got left is a section on the dot product, a section on the cross product, and equations of lines and planes, which is going to be a little bit of new stuff. Quadric surfaces, which is kind of hard to visualize. And then, I screwed up. I did cylindrical and spherical coordinates already, but we just did polar coordinates and it was a good time to do it. They don't put that till the end of this chapter. Okay. So what I'll be assigning between now and next week is pretty much all of chapter 2. Because we've covered most of the first 4 sections implicitly. Unless you have more trouble with it than I expect you will. All of chapter 2, except for the quadric surfaces, which we'll save for a fresh week. So I recommend that you get the things done on, the next 2 sections, 2.1 and 2.2. I don't think we're going to challenge you. You're going to take a little time to do it. You want to think about what you're doing. 2.3 and 2.4, I'll take a closer look at what the problem assignments are, but I think you're probably not going to have time between now and Thursday to work much further than the first couple of sections. If you can, it wouldn't hurt if you got time. But that would leave you a fair amount of stuff for the weekend. I might save the actual assignment, cylindrical and spherical coordinates, until next week, but you probably ought to at least get a start on it. Okay. So we'll see where we go. Right now, see if you can't get the problems in section 2.1 and 2.2. I don't think you're going to have to do a whole lot of. Got a question I can answer quickly. Got a meeting at 2 o'clock, but up to that point.
How do you check homework?
Usually while you're doing a quiz,